Some of the material from this talk is in former AIG publications, and as Graham alluded to, I'm now in the process of writing the new edition of the old Corbett and Leach short course manual, which will be full of colour rock photos this time and available on the AIG website, according to Madam President, when we get it done. So this talk, Anatomy of Epithermal Gold, Silver and Porphyry Copper Gold, I suppose some of you have sat through my talks before. It's empirical. My science is built up from the observation of lots of deposits, and as such it reserves the right to evolve as you look at new systems. So, you know, we're looking at a whole bunch of stuff around here. Last week I was up in here in far northern Chukotka, and I assure you Adelaide winters are far more pleasant than Chukotka summers. We had 7 days of snow. Right, so this is this week's version of the Corbett model, and this is what we're going to be dealing with, the anatomy of these systems. I've got to go back to where I'm supposed to be, I get excited. So in this anatomy, what we're talking about is a magmatic source. I'm a magmatist, and we're going to talk about a porphyry system in an apophysis that's polyphasal, and in our epithermal regime that's, say, the top kilometre of the crust, Terry and I divided, as has been the norm then, between low sulphidation and high sulphidation, and we'll explain those in a little while. The Carlin type deposits we put in amongst low sulphidation, and Terry and I divided low sulphidation between what we are used to seeing in magmatic arcs, because we'd been working in the Philippines, Papua New Guinea and Indonesia, and the banded vein systems, which are more typical of extensional environments and are what are mostly in the published literature, where they're called adularia cerussite. More recently, people have coined the term intermediate sulphidation, which a number of us don't agree with, and you would possibly call the lower temperature end member of those intermediate, but I'm going to stick with the original Corbett and Leach classification. So here we've got a magma source, we've got a bunch of high-level porphyry intrusions, and up here we've got subvolcanic domes. A major aspect of this anatomy is the progressive evolution of fluids from down here up to here, and a change in the style of mineralisation. And the reason why we're dealing with this anatomy is that if we might think we're clever enough to look at some parts of the system that aren't so well mineralised and then target parts of the system that are better mineralised. So the difference between high and low sulphidation. If you want to go to the academic literature, you can talk about the sulphidation state of the ore minerals, but I'd rather talk about the ore fluid and the ore minerals. So a low sulphidation system is a neutral fluid, commonly dominated by the entry of circulating meteoric waters, which, to put it simply, entrain a magmatic component, and we give ourselves our different ore types, which I haven't mentioned thus far. In this group here, we're going to go from quartz sulphide up to carbonate base metal, and then up to epithermal quartz gold silver. And on this side, we're going to go up through polymetallic silver gold. So these two are related. These are the fellas that we see in the Southwest Pacific, and these are the ones I'm going to show you mainly in the Andes. And then that fluid further evolves to our banded chalcedony ginguro systems, and we'll look at examples of these and it'll all become very clear in a minute. So our low sulphidation systems are a near neutral fluid dominated by a serious component deposited from circulating meteoric waters. And when we're dealing with low sulphidation vein systems, what we commonly see are these banded veins. And so clearly a banded vein is a band of this mineralogy, that's Freibergite, the silver-rich tennantite tetrahedrite, some base metal sulphides and some rhodochrosite, or some chalcedony, or this black stuff that's called ginguro that I'll explain later. So each of those bands is a new episode of mineral deposition. And if it's a new episode of mineral deposition, it's different, therefore it's probably a different fluid. And this model helps to explain one of the problems in low sulphidation vein systems, in that we have radical differences in ore grade in different parts of the vein. So here's our magmatic source again, which is the source of heat and metals. And our fluids, our ore fluids, go into our structure and we deposit our banded vein up here. We may have shallow circulating cells of meteoric dominated waters, and they don't come anywhere near our magmatic source for our metals, and so they'll deposit clean quartz, typically chalcedony in this case. Some of our meteoric fluids might circulate deeper, entrain a magmatic component, and in our vein here we've got some quartz with disseminated sulphides which might have some low-grade metals. Every so often our structure taps our magmatic source, opens big time, and so we get a magmatic fluid that comes up here. So we've got our banded vein, and this part here is barren, and this part here that's much narrower with our magmatic component is mineralised. And so that answers an issue that I commonly deal with young geologists, which is, Greg, why do we have this big wide quartz vein here that's barren, but this tiny little fella that's mineralised? Within these veins we've got different fluids going on. And so when I visited Arkaroola years ago, here's Justin, and we've got these beautiful big quartz veins, and they're barren because they're just circulating meteoric waters. But elsewhere in that district we do see some evidence of what's probably a magmatic source. I reckon that Mount Pater was a diatreme. So, but another corollary of that is that recently in Patagonia we've got several instances, Cerro Moro, Huevos Verdes, another one, where we see these barren quartz veins at the surface. So we're looking up here, but elsewhere in that system we've got mineralised veins at depth, and that's part of why we're trying to understand our anatomy. If we've got these barren fellas, will there be something mineralised nearby? So let's go through some of these. We're going to start with leaving an intrusion source, and we're going to look at the quartz sulphide gold plus or minus copper first. Here we have gold in commonly coarse crystalline pyrite in these instances. The gold is on fractures and grain boundaries, so these fellas typically have good metallurgy. If we're at a high crustal level and low temperatures, we'll have a low temperature mineralogy of marcasite, opal instead of quartz, and sometimes we have what we call in Spanish silica gris, which is grey, fine grained chalcedony with fine grained pyrite in it, and this stuff will commonly have difficult metallurgy, which is gold encapsulated in the fine grained pyrite in this case. These sorts of things, you might only have grades of 1 to 5 grams if you're lucky. Occasionally you'll get a high grade. This stuff from Kensana was 300 grams with a bit of hypogene hematite we might touch on later. A good example of a fine grained one with difficult metallurgy, of course, is Lee here. Here with side-looking radar on the island and offshore seismic, we see what was a stratovolcano that collapsed sideways only 100,000 years ago, and we took a kilometre off the top of an active porphyry. So these ore fluids were rapidly cooled, and we've got this quenched Arsenian pyrite. It's high grade, but the gold's encapsulated in the Arsenian pyrite, and so it's a roasting job, and I won't show you a current photo because it's not nearly as nice as the Caldera as it was in '84. There's our camp by the beach, fishing, swimming, and all the malaria you needed for the rest of your life. At deeper levels, we see chalcopyrite, hence the plus or minus copper, pyrrhotite, and hematite magnetite. So this has an anatomy. We can either be high level or much deeper. Some good examples would be Round Mountain, which is a head grade of 0.8 grams per tonne, but I've produced about 9 million ounces of that. It's gold in this cubic pyrite, brilliant metallurgy, dig it up, stick it on the leach pad. And talking of leach pads, we see at Sleeper, which is famous for its bonanza gold, an early similar quartz pyrite event, and there's the leach pads there. A few examples of these in Australia would be Nolan's, Mount Wright, which is in a rhyolite dacite dome, and even Paulson's, which is marginal to a batholith. But we'll see these all through central western New South Wales as well, but I didn't give you a lot of those examples. The quartz sulphide systems, as well as going up high into lower temperature with opal and marcasite, these actually represent the link to our porphyry systems, where we have sheeted veins such as at Cadia or the Maricunga Belt, which are marginal to porphyries, or the old D veins. Colin will remember the Gustafsson and Hunt classification of 1975. So they're D veins that are marginal to porphyries fit into this quartz sulphide classification. So we're immediately outside a porphyry source. Now, the quartz sulphide vein systems are a great money spinner for me, because I see plenty of examples where people have got soil samples, anomalous soil samples and rock chips at the surface, and nothing when they've come to drill it. And these systems are commonly worked by artisan miners, whether I'm in Chukotka in Russia, where I was a few weeks ago, Patagonia, Bolivia, or Papua New Guinea here. These are the guys that most commonly give us near-surface supergene enrichment, because the gold is easily liberated from this pyrite under weathering. And as soon as I see our boxworks after pyrite, I get that sinking feeling in my stomach, because in this case here, which the official name is Pollux, my London client didn't actually appreciate me calling it bollocks, but there you go. At the surface we could get 300 grams. These little pyrite boxworks, if you look carefully, you can see little bits of bright yellow supergene gold in them, 2 grams in a drill hole. See this time and time again, where we get supergene enrichment at the surface, a bit more at the base of oxidation, and you drill them and you get low grade. So these are interesting, they're great bulk low grade targets, but there's always a note of caution. This one here, Tuiri Ridge, there were 5,000 illegal miners until the Indonesian military persuaded them to go elsewhere. Barely a gram in a drill hole. So, a relative of the quartz sulphide are the Carlin-style sediment-hosted replacement gold deposits, where our quartz sulphide fluid has entered a reactive rock, an impure limestone or a marl, and so we have these manto-style sediment-hosted replacement, and you can see the stylolites and what have you here, where we've replaced our permeable host rock, 2 grams in that, but in a feeder structure up to 15 grams in Meikle. They occur in lots of other parts of the world apart from Nevada, but we don't see them so much in Australia. Now this is the part that Graham particularly wanted me to talk about tonight, is moving into our carbonate, base metal and polymetallic gold deposits, which are also my favourite. Here we've got high level intrusions, and what happens is as our high level dacites or rhyodacite cool, they let off carbon dioxide. That carbon dioxide rises and we get these blankets of bicarbonate waters, and they commonly vent to the surface as travertine deposits we see in many magmatic arcs. But later, as our ore fluids are coming from our magmatic source, our ore fluids enter this regime and mix with these bicarbonate waters, which are weakly acidic and oxidising, and they destabilise the complexes carrying gold and deposit our mineralisation. So these deposits, which are by far and away the most prolific producers in the Southwest Pacific, all have the same paragenetic sequence. We've got our early pyrite, which might have a bit of gold in it, and then we've got more sphalerite than galena. There's a tiny bit of galena there, and then we've got late carbonate. So this is Chilean, and here's porphyry with a bit of, because this vein's growing inwards, a bit of early pyrite, our base metal sulphides, and then our later carbonate. So, you know, some pretty important deposits of porphyry and Chilean. Antimok was 4 million ounces, Akupan 10, and there's a bunch of others too. But let's move through these. In the Southwest Pacific, these are gold producers because they're in andesitic magmatic arcs. I need to remind us that mineral deposition occurs by the mixing, I'm not allowed to move, mixing of these two fluids. So if you've just got the sulphides, you'll get a bit of grade. If you've just got the carbonate, you'll get nothing. And in this example here, I got all excited when I found these carbonate lodes at the surface at Keramengi. The carbonate's got nothing in it. The Quartz pyrite's low grade. The ore in here is where these two fluids have mixed and given us the carbonate base metal gold system. These systems are zoned. You can have a lot of fun with these and you can prospect them out looking at the zonation. The first one we're going to look at is the zonation in carbonate, which basically this zonation is a reflection of the acidity of the bicarbonate waters. If they're more acid, we'll get siderite, and of course by the time they're neutral, we just get calcite. And here's two trays of core, two adjacent trays of core from Chatri in Thailand. And there's very fine grained galena sphalerite pyrite here, but this is of course rhodochrosite. And where I don't see siderite often, where I do see it I get really good grade. But I more commonly see rhodochrosite. Where I've got my rhodochrosite I've got high grade, and as I move down through kutnohorite, dolomite to calcite, you can see how my grade drops off dramatically. So it's the rhodochrosite I'm typically looking for, and of course our prospecting tool in these systems, I'm scratching around looking for my manganese oxide. That's Mount Kari. He's obviously mining a bit of supergene gold in this, and that's the discovery outcrop from Hidden Valley in Papua New Guinea. Both, this one's now in production of course, both carbonate base metal style, and there's Wow, a very famous older one. The other aspect that's zoned with our anatomy is the sphalerite colour. Sphalerite colour is an indication of our iron to zinc ratio, which is an indication of our temperature of formation, which is an indication of our depth of formation. So at deeper levels, higher temperature sphalerite tends to be black, iron rich, and as we move to higher crustal levels, we're going to go up through red to yellow and to white, and sometimes even clear. Now, I'm pretty enamoured about white sphalerite, and I'll explain that later because I really do like the higher crustal level, low temperature systems, but they're all mineralised. So we've been talking about the carbonate base metal systems which are developed in the Southwest Pacific, and they're gold rich, and Terry and I coined that term in the early 90s. Since then, I then went and started working in South America where there was already a terminology, the polymetallic silver gold systems, and of course these are quite famous. They funded the Catholic Church in the Spanish Empire for several hundred years. This one, the gold's much deeper down, several hundred metres at the bottom of the hill. This one, Cayoma, was mined by the Incas, the Spanish, my client, and then they hocked it to somebody else, and it's still going. Same mineralogy to a certain extent, our banded vein with our galena, sphalerite, quartz. You can see some pink rhodochrosite there and all that black colour at the surface is our manganese oxide. But a lot of our silver is coming in with silver sulphur salts, which I'll show you in a minute. These vein systems were ignored for many years by the majors because they were regarded as veins and not much interest. But for the juniors, they're great company makers. Fresnillo, a non-outcropping ore body in Mexico, has made that company. Palmarejo, Australian company Bolnisi, the shareholders walked away very happy then, and I still work for the directors. Another one, Carani in Peru, and San Cristobal in Bolivia. These continue from Mexico down through Ecuador, Fruta del Norte is one of these, into Peru and right down to Patagonia. We might see an example from Patagonia later. They're in extensional terrains, typically listric faults. There's a couple of geologists somewhere along this listric fault, but I've lost them. There they are, they're over here. So in these, we only see mineralisation in the steeper part of the listric fault. These systems might vary to include things like Mangana, where we've got high-grade silver with tenantite tetrahedrite here. Or I remember this one, which is the Ducat field in the Okhotsk magmatic arc. Now there's Kamchatka, so we're up in here. Kamchatka's about the length of New Zealand, and I got the high school atlas out, and from Magadan to Kupol, where I was last week, that's Sydney to Whyalla. And I'd much rather fly Sydney to Whyalla on Qantas than on a Russian freight plane, but there we go. Here's our quartz, here's our rhodochrosite, lovely yellow sphalerite, silver sulphur salts here. This thing is basically a silver mine, less than a gram gold and 500 grams per tonne silver. So you do have silver-rich variations in amongst what could be described as a carbonate base metal system, but I've popped into the polymetallic silver box. Bowdens in New South Wales would be another silver-rich end member of that group. So it's transitional. These things display a vertical zonation. Obviously this is a slide for Patagonia. I've got our bicarbonate waters. I've got a competent andesite, an acid sulphate cap. In our listric fault, we're going to look at copper-rich at depth, going up through lead, zinc, silver, and then possibly gold-rich at a higher crustal level. This example from Mexico, we've got about 1 kilometre of relief, and we've got porphyry manifestations down the bottom of the hill, post-mineral ignimbrite up the top, but this stuff here is copper-rich at a deeper level. Most of these systems we see our yellow sphalerite. Here's some silver sulphur salts here. Again, here's some Freibergite and our rhodochrosite. Most are as banded veins. As we move to the very highest levels in these systems, and this is one in Mexico, one in Patagonia and one in Thailand, we have the same, and I've seen it in Russia too, same unusual mineralogy of pyrite, white, low temperature sphalerite, and sometimes, white low temperature sphalerite, argentite, acanthite, the low temperature form, and sometimes a bit of hypogene hematite. These things have the bonanza gold grades with the argentite, acanthite. And these evolve because what happens, we've gone from our copper rich to our lead zinc rich to these ones here, which are the silver rich, and as we bring in more meteoric waters, our ore fluid is going to evolve into this type of vein we're going to see in a minute, our banded chalcedony ginguro vein system. So we're going to evolve from our polymetallic up into these other fellas, which we'll do now. So our epithermals at the top of this figure, so we've in one side for our carbonate basin, we're going up that way in our magmatic arcs such as Indonesia, Papua New Guinea, Philippines, and in our more extensional settings such as Mexico, Peru and Patagonia, we're going to head up in this direction. And these two epithermal end members are quite distinct. Occasionally you do see them in the one property, but they are quite distinct. These guys have got high fineness free gold and very little gangue, and these guys have got low fineness gold with electrum and a lot of gangue. So let's go up this trend first. Of course, the classic example is Porphyry Zone 7 that I mapped as a piccaninny in 1980. Here's our early carbonate base metal mineralisation, a great big pyrite vein, and it's cut by these little fractures which have got green roscolite, which is up in here too. And so here we have our free gold, bonanza grade free gold, with hardly any gangue, just a little bit of quartz, and that's in zone 7 here. And it's interesting, more recent, our carbonate base metal is high temperature. It's got pyrrhotite and dark sphalerite, and this event here is related to a younger, higher crustal level felsic event where we think we've had thrust erosion during mineralisation. And curiously, Mount Kari, 20 kilometres away, could well be the top off Porphyry because drilling finishes in a thrust. But I digress. Emperor Gold Mine is on the margins of a caldera. We've got our early quartz sulphide event here in our flatmakes, and this week's model is the flatmakes are formed by reactivation of the bedding planes around the margins of the caldera. So we've got these blocks that have each got flatly dipping mineralised structures at slightly different angles. That is overprinted by the same bonanza grade free gold with a little bit of quartz plus roscolite, and here we've got some tellurides as well. Round Mountain we saw before with our quartz sulphide event, and at Round Mountain there is a bonanza gold event. Here's a breccia with quartz clasts and gold matrix, and this is a plate of breccia. To this day I wish I hadn't got the photo of the dunny in the background, but there you go. Similarly, Sleeper, which is famous for its free gold, this is a high fineness bright yellow free gold. Just remember that when we get to the next slide, and you might want to remember later that there's a whole bunch of kaolin floating around in this. Because as we get into these guys, we're dealing with a different mineralogy. These I'm calling chalcedony ginguro gold silver with Dave Cook's blessing, because I don't like the old terminology which was adularia cerussite, because it's not cerussite, it's illite, and the adularia isn't always there. Chalcedony ginguro, well, ginguro is a Japanese word because in the 19th century Japan was funded by the mining of these deposits. Hishikari, of course, is one you know of now, but Sado gold mine began production in 1454, and the shogunate of Japan was out on Sado Island for several hundred years because that was the money box. So these guys are made of chalcedony, our ginguro bands, which are fine pyrite, electrum, bit of chalcopyrite, silver sulfur salts, and a bit of free gold. We have our boiling minerals, quartz after platy calcite, and a bit of adularia there, but they're quite distinct and removed from our ginguro bands. The ginguro bands host all the mineralisation. You can see a bit of free gold in this example from Kamchatka, and here's a specimen from Hishikari which is 948 grams. So the model I was talking about before, if you selectively sample this ginguro, you might barely get a gram. You'll probably get nothing. This chalcedony, most of the ore is in these discrete ginguro bands, and in my model they're distinctly removed from the quartz after platy calcite and often the adularia. I've sampled buckets of these boiling related minerals and got no gold, so I'm not a boiler. I don't believe in that. These systems are vertically zoned. Here's our structure. We've got our, well, horizontally zoned too. Here's our alteration going from illite out to illite smectite to smectite, and our vertical zonation might be an acid sulfate cap at the surface, and we'll revisit these later. A sinter with some cinnabar, our polyphasal eruption breccia with some sinter and wood clasts, all barren, and then we'll pass down into a bit of low grade in our sheeted vein system such as McLaughlin, but all the mineralisation is normally in our fissure vein here in our main structure, which has a decline in gold grade as we go into a deeper polymetallic vein system, as I mentioned before. So that's the end of the system. So we've done our low sulfidation epithermal vein systems, albeit quickly. We see the anatomy as our fluid flow paths in those two different directions, from the ones that are dominantly in a magmatic arc to those that are in a back arc setting. These are more removed from our magmatic source, whereas in these it's quite common to see high level felsic intrusions. Porphyry systems. So we're going to go deeper down now. I'm going to talk about a magmatic source and our polyphasal intrusion system. Here's our traditional model from Spencer Titley or Richard Silito, where we've got a stratovolcano and our porphyry underneath our stratovolcano. That still holds. There's nothing wrong with that. But when we start looking at some of these more recent discoveries, Grasberg, well, Bigham Canyon's an old one, Olgut, Tolgai and Cadia, none of those are in their own volcanic pile. Cadia's out in the shelf sequence, Grasberg's into a bunch of metamorphic rocks, so they're removed from a stratovolcano. So it's time to start thinking about the importance of structure in our porphyry systems. And this old model that you would have seen in 1990, whenever it was in Ley. Here in this model we've got two main sets of structures in our magmatic arc. We've got arc parallel structures, which are commonly terrain boundaries, and we might have transfer structures that allow the arc to change the subduction dip or the rate of subduction to change, but segments our subduction zone. And so we see each of those as controls to porphyry systems. And of course, in northern Chile, we've got the Fire Oeste or the D'Amico fault, and a whole bunch of these porphyry systems, El Salvador down here and Chuquicamata, are along that structure, and of course prospecting along that structure allowed David Lowell to find La Escondida back in the 70s. I'm still working for Codelco up in here, and we'll be prospecting along that structure for a lot longer, because that's where a large proportion of Chilean porphyries lie. In New South Wales, we have an arc parallel structure in the Gilmore Suture with mineralisation along it, but a better example is our transfer structure, which moves a bit according to where your prospect is, so you can get it on it. But of course, there's the Cadia system, which is clearly aligned along that structure from the new ore body, Cadia Far East, out through Cadia Hill, the sheeted vein system, to the Ridgeway Porphyry system that we'll look at tonight. The crux of the issue, well, there's two cruxes. The crux of the issue, number one, with porphyry systems is bleeding fluids from a Yeovil style batholith, which is low grade and sub-economic, up into the apophyses, typically around the top of a polyphasal system, where here we've got several different events of stockwork veins to give us something that's economic, and then sometimes up into a wall rock porphyry such as Cadia Hill. And the other crux of the system is we've got so many overprinting, alteration and mineralisation events in a porphyry system that it often looks like a dog's breakfast. But we're lucky, because I worked with Terry, who'd worked in the Philippine geothermal systems that are driven by porphyries that are active now. So we've been able to put time in. And then we start putting time in, it all becomes a lot clearer to me anyway. So here's our magmatic source, and the first thing we're going to do is our stock-like, spine-like apophyses is going to pop up, and we're going to have our prograde alteration introduced as a conductive heat transfer. And this is going to give us our potassic grading out to our propylitic alteration. So our potassic alteration, which is higher temperature, is dominated by secondary K-feldspar orthoclase in the matrix to this intrusion, secondary biotite replacing primary hornblends and biotite in this case, and of course lots of magnetite. So there's our first event. Now let's look at some of the, if this is sodium rich, we might have albite such as at Namosi or in central western New South Wales. Our first veins using, now that the vein classification is a bit of a circus, but we'll do our best because everybody's had a go. In the Gustafsson and Hunt 1975 classification, we've got our tigmatic high temperature A veins that formed while the intrusion was cooling, and these are barren. But in the Silito classification, we've got linear, what I call granular A veins that commonly contain chalcopyrite and bornite. These are mineralised, and they're going on during the alteration because here we see some orthoclase as a selvage to these. In the Mason classification, we've got M veins, which are quartz, magnetite. They're commonly laminated like this fella here from Copper Hill, and they are dominated by bornite rather than chalcopyrite. These two examples are sheeted, and I like sheeted veins because they can transport mineralisation from our magmatic source at depth to a higher crustal level where mineral deposition occurs. Notice this one's cut by a later vein. We'll get on to him in a minute. Our potassic alteration grades outwards to our propylitic alteration, actinolite closest to our intrusion, going out to epidote, going out to chloride. So this alteration zonation is a vector that we can use when we're looking for porphyry. So if I'm seeing chlorite carbonate, I'm not terribly interested. Epidote, I'm starting to get a bit warmed up, and if I'm seeing actinolite in the drill core or in the surface, I know that I'm not all that far from the potassic alteration, and it's starting to get a bit prospective. So that's a very real vector. Talking of vectors, I'm going to get to these fellas in a minute. So our porphyry has been emplaced and it's starting to cool, and we've deposited some mineralisation. As it continues to cool, it lets off a spurt of magmatic volatiles. And Terry and I use the term barren shoulders to describe these. This is lookout rocks, where we've got these series of structures here in the Ohio Creek porphyry coppers down here. Here's the Horsa Val porphyry copper here, and here's the Equator Bomb barren shoulder. So these are a spurt, or they're deposited from a spurt of magmatic volatiles that have come up here. They have a core of silica, and they zone outwards as high temperature advanced argillic alteration. They're barren, but they do occur in the region of porphyry, and we might try and use them as a guide when we're prospecting. But here's one of Terry's geothermal slides. Now these are geothermal drill holes. That's a 1 kilometre bar graph. And so this zone of advanced argillic alteration, one of those barren shoulders, is at least 2 kilometres, 2.5 kilometres deep. So these aren't my favourite vector. Yes, they're in the region of a porphyry, but what I find is they're bloody hard to use as a prospecting guide because your porphyry might be a long way away. Plus, if those fluids then come into a permeable host rock, we end up with what we call a lithocap, where you get a great expanse of this sort of alteration and you don't know quite what you're doing. They are a vector, we can use them, they're part of the story, but they're not easy. Isn't that a lovely volcano? So, our porphyry is still cooling, and we get another set of veins here which are called B veins in the Gustafsson and Hunt classification, which are characterised by centrally terminated quartz and then sulphides, typically chalcopyrite, pyrite, that come up the middle. So the sulphides are coming in after the quartz, and that's part of this story. What John Prophet would call a C vein, Gustafsson and Hunt gave us A, B and D. I don't know what happened to their C, but someone else has used it afterwards. When I visited Grasberg, they were mining 4% and 4 grams, and when we cut this rock open, we see these sulphide bands that are coming straight across. So the C veins are a later sulphide event, and they're basically the source of the sulphides in the B veins, and we see them here as cross-cutting veins at Ridgeway. So that's our pro-grade porphyry anatomy, and at this time we've had convective cells moving out from our porphyry, and they've been taking our volatiles and they've been moving out. Now, as our porphyry starts to cool, well, hang on, as these volatiles have been going out, we've been having SO2 rising up above our porphyry, and we often end up with a sink up here of SO2, which might condense, oxidise, and basically give us H2SO4. As this porphyry starts to cool, we're going to have what Terry would call drawdown, and these acid waters then collapse on our porphyry. And so what happens then, we have our phyllic alteration, which is collapsing down on our porphyry. Now this is silica, cerussite, chlorite, pyrite, and a bit of carbonate anchorite. So this is a retrograde event. Here we see our cerussite on the margins of a B vein, and it's buggering up our magnetite on that contact, and it's buggering up our magnetite there. There is a technical term, but I can't remember it. And so this is associated with regional magnetite destruction, and it's pyrite rich. Remember that, because we need that pyrite later. If these fluids are really acid, we might get an advanced argillic zone which morphs into part of that lithocap classification with some allanite, diaspore, pyrophyllite. It's not common, but it does occur. What's more common is some SCC alteration, which is silica, cerussite, clay, where we're getting an argillic overprint. And if you look carefully, you'll see in these systems that here's our original silica, cerussite, pyrite, and you can see all this clay in between it because it's just a clay overprint and it's a separate event. But all of those are magnetite destructive. So when we're dealing with our magnetic data, we've got to remember that if we've just got our prograde system and we're up above it, we might just have a spot high. If we've got a ganumbla and we've eroded down to that level and we don't have a retrograde system, we're going to have a donut. But if we're in Chile, where I'm working at the moment, we've got bugger all magnetite signature left because it's been destroyed by our phyllic alteration. So you need to bring your alteration zonation with time into the discussion when you're dealing with your interpretation of your magnetite. And remember, if anyone's got a mental picture of the old David Lowell and Gilbert model, they go from potassic to philic to propylitic because it's a function of the overprinting. And those early models didn't have time in them. The last event is, although this is cooling, this thing here is still letting off metals. So we have the last event of veins, which are D veins, and here they are. We've already seen them in our quartz sulfide classification in the low sulfidation systems, and we'll see them in the high sulfidation systems again. But remember, aspects that are important we still need to consider is our polyphasal intrusion event, and sometimes that polyphasal intrusion event continues to be post-mineral. Many intramineral intrusions are low grade, or it might be cut, such in the case of El Teniente, the world's biggest porphyry, by a post-mineral diatreme. So what's important to me here is the best porphyry systems are polyphasal. This piece of rock from Ridgeway, you can see there's this vein, it's cut by that vein, they're cut by these epidote veins, and they're cut by post-mineral quartz carbonate. The best porphyries are polyphasal, where we've had several events of mineralisation. So when I'm logging a porphyry, I'm looking for evidence of a polyphasal system, where I might have xenoliths, contacts between different alteration zones. I might have here, I've got a contact between two intrusions, or here I've got residual early A veins that haven't been consumed by the later event. These two porphyry systems, La Arena in Peru and Warangiri in Indonesia, all the intrusions were the same composition, so it was really difficult to identify the polyphasal aspect. So these residual A-type quartz veins was a bit of a clue. But for me, an important factor in porphyry exploration is to be looking for polyphasal intrusions. And if it's not polyphasal, it commonly won't run. Now, I mentioned we had to remember the pyrite. That pyrite oxidises in the weathering environment to give us lots of acid groundwaters. Those acid groundwaters dissolve our copper, and then that copper is then redeposited at just below the base of oxidation, overprinting our earlier prograde porphyries to form our famous chalcocite blanket. And although we might not see so many of those in our Southwest Pacific porphyries that don't have a prominent retrograde philic alteration zone, certainly in the Andean systems that's critical to forming our high-grade copper zone here, which can be mined earlier and put it into production. But of course, systems like Octeti, it was critical too. So there's our supergene blanket, formed only in the systems with a good retrograde philic alteration zone. So far, we've looked at our low sulfidation systems here, grading out from our intrusion source, which here might be a porphyry or it might be a bunch of high-level subvolcanic intrusions. Here's our polyphasal porphyry. In this side, here's our D veins. On this side, we're going to have the same thing happen. We're going to form here our high sulfidation system. These are not well developed in our part of the world. There's a couple in Australia, both went into production, but they're not big. Mount Carlton's an odd one, which we'll look at in a minute. Mount Kazi was high grade, and of course, probably Lepanto's the most significant in our part of the world. There's some new ones in production, such as Matabe. But the home of these, where I work on them most, is in South America, where we've got some giants like Yanacocha, Pascualama, which we'll have a glimpse of. So this is where most of my work on these has been. Now, whereas with our low sulfidation systems, we were entraining groundwaters and a circulating cell of meteoric magmatic fluids, our high sulfidation systems are entirely different. Here we have, I'd love to go to the screen, but I'm not allowed to. Here we have a bubble of hot magmatic volatiles that leave our magmatic source. That bubble rises rapidly up this structure. As it rises rapidly up that structure, it becomes depressurized. As it becomes depressurized, the SO2 comes out of solution. That SO2 then oxidises to give us H2SO4. So we've started down the bottom here with a hot neutral fluid. As it's risen, been depressurised and oxidised, it's progressively become more acidic. So by the time we get up here, we've got a fluid that's hot and got a pH of about 1 or 2. That hot acid fluid then reacts with the wall rocks and progressively becomes neutralised and cool, and we have a characteristic alteration zonation. Now try doing that in Spanish. It's a pleasure to do that in Adelaide in English. But that's the model where these form from a hot acid fluid. Now it's important that that hot acid fluid has no reaction with the wall rocks or circulating cells of meteoric water in this level. So there's this bubble that rises and progressively becomes more acidic. So when it reacts with the wall rocks, this fluid of pH of 1 or 2, it rips everything out of the rocks and it gives us a characteristic texture in the centre of the alteration zonation that we call vuggy, because here it's leached out all the feldspars, or residual silica, because quartz is, and a bit of rutile, quartz is basically all that's left. So here our fluids are pH of about 1 or 2 and pretty hot. Here it's grading and it's gradually being cooled and neutralised, and we produce an alteration zonation that basically grades out from alunite to diaspore porphyry to dickite kaolinite. And here's an example of that alteration zonation. I've only put one in. Here's a structure at Nina, and the fluid upflow is up here, which would be, here's our long section, here's a cross section down here. So our fluids come up here, float along this structure. So here is our vuggy silica in the middle, grading out to our alunite and our porphyry. And it's important to note here that the vuggy silica doesn't outcrop at the surface in this segment, because there's a twist here. Now I'll come back to that. There's a twist here. This fluid actually breaks up into two phases. The volatile rich phase, which does this, and the liquid rich phase, volatile rich phase that does this, and the liquid rich phase that comes later and deposits mineralisation. So it's important to note that the mineralisation's only in the vuggy silica, and so if you were prospecting on that cross section, you wouldn't have found it. Now that alteration, has anyone seen this figure before around the traps? I don't have time to explain it. No one's put their hand up, you buggered. This is Terry's pH versus temperature figure. So we're going from acid to neutral, and we're going from cold to hot. So our porphyry, which I talked about, our biotite, actinolite, K feldspars down here, going out into our inner propylitic alteration with epidote, going into our outer propylitic alteration with smectite there. Our low sulfidation system I talked about, grading from illite to smectite in that direction going up there. Our porphyry system, there's our cerussite, which is our phyllic overprint on our potassic there. But for these systems, here is the trend of that barren shoulder, leaving the intrusion, travelling up here through hot mineral assemblages, andalusite, corundum, and getting up to here. Here's our high sulfidation system, and we have a different mineralogy if we're dealing with a deep structurally controlled system or a higher level lithologically controlled system. So, as I mentioned, this system breaks up into two fluids. The early volatile rich fluid doesn't normally deposit much mineralisation. That's followed immediately by a liquid rich phase of the same fluid, and that deposits our mineralisation. And here our mineralisation is characterised by energite, or its low temperature polymorph leuceinite, and a bit of pyrite. Here it might be as a vein at El Indio, a breccia matrix such as Yanacocha, a fluidised breccia, or filling our vugs. Also with that, we have a second generation of alunite in our breccia matrix with energite, some barite, and locally a bit of sulphur if it's sufficiently low temperature. Permeability control in high sulfidation epithermal gold systems is either by way of breccias, structural or lithological. The most common breccias are phreatomagmatic or diatreme breccias that have been driven by the same magmatic source as our mineralisation and are typically pre-mineral. We've got a banded tufaceous horizon high up in Pasqualama at about 5,000 metres. Nearby, here's a mill breccia in our diatreme at Veladero, but our mineralisation typically comes later, and at Yanacocha we see our sulphides in the matrix to a diatreme breccia, or at Lepanto it's coming up the margin as a fluidised breccia just outside it. Our lithological control, Perina would be a good example, where here we've had a Fiamme tuff, and those Fiammes providing primary permeability have been exploited by our acid fluids to give us secondary permeability, and so our ore system is this subhorizontal zone here. And look, it bottoms. This is that model whereby our fluids need to evolve, and these systems all bottom because those fluids need to evolve to give us our high sulphidation system. Another lithological one would be La Coipa, where we've got our volcanics sitting on top of some slates. The slates have got low-grade veins in them, but once those fluids hit the volcanics, they blossom out and give us our high sulphidation system. Structural example, the best one, of course, is El Indio in Chile. Here's a sigmoidal loop that Stan Caddy first mapped. I mapped these ones here, which are a bunch of plunging ore chutes. Plunging because there was a mixture of strike slip and dip slip deformation, and each of those ore chutes is sitting in a flexure in this through-going structure. But the most common scenario would be the intersection of a structural feeder and a permeable lithology. Sipan in Peru, we have a wonderful example here of, here's our structure. Here's our flooded Fiamme tuff, but here's our original Vuggy silica. It's been brecciated, and there's our sulphides come into the breccia matrix, textbook geology. But the issue here is, when I visited Sipan, they'd mined all the oxide ore and they'd just hit the sulphide ore, and the question was, Greg, what do we do now? And the answer was walk away, because these systems are typically low grade, and in the sulphide ore they're horrible metallurgy. And if you go back, if you go back a few, there's our smelter at El Indio. You've got to have El Indio type grades to pay for the cost of the smelting, and that's not normally the case. These things are not an ideal target because they are only best mined in the oxide zone. Not all that often can you mine the sulphide zone, in which case you need grade and size. So this one didn't go anywhere. But you can, there is some hope. I mentioned before how our fluid was evolving from acid to neutral. Sometimes it'll evolve all the way out here to lower sulphidation. And at El Indio, there's our sigmoidal loop, there's the Viento vein system that I mapped. We've got our early energite event and the Bonanza gold event that you've probably read about, that St Joe mined as the direct shipping ore. There's all the free gold there. Some of us will allege as a low sulphidation epithermal style. So this one we allege has evolved from high to lower sulphidation. And in the Viento vein system that I mapped, going from south to north, at the southern end we had energite leuceinite, which is typical of high sulphidation, but suddenly in the middle we had a carbonate base metal ore with galena sphalerite rhodochrosite, and right up the northern end we've got our classic epithermal quartz gold silver with free gold in quartz. So there we had a good example of one evolving from higher to lower sulphidation. So I wasn't at all surprised to see some Mount Carlton core in Queensland, where we've got our original silica alunite, Vuggy silica, a bit of energite, but then all of a sudden it evolves out to yellow sphalerite and high-grade silver with silver sulfur salts. Cuivar in Argentina would be another example, and I could give you others. So it isn't unusual for these guys to evolve to lower sulphidation, and where it does evolve to lower sulphidation, it'll have higher grade and better metallurgy. And there's one other trick you can pull, is that the tops of many non-eroded high sulphidation system are capped by a steam heated blanket. It's not unlike an acid sulphate blanket you'd get above a low sulphidation system. Our H2S is oxidised to give us cool acid waters above the water table. This is the blanket at Pasqualama. I'm standing, now this was 5,500 metres when Glenn Van Kerfort and I remapped it. And so I'm standing on the Chilean side and that's the border between Chile and Argentina. So that's our steam heated alteration, which is a mixture of powdery alunite, kaolin, cristobalite, bit of sulphur, total textural destruction. But if these oxidising fluids do re-enter the system, they will promote gold deposition, and sometimes that happens, but we won't go into that. So what I've done is try and talk you through this models figure. These PowerPoints will be on the website. There's a bunch of papers on my website, or the AIGs, that you can read for a bit more detail, or you can wait until I finally get the new manual written. But the story is we've got our fluids evolving from our magmatic source. There's a large part in our fluid evolution as we go from our intrusion-rich system out to our margins, where we have an increase in gold grade as our fluids evolve and a change in our style of veins. We try and understand the anatomy because there are cases where we can prospect below acid sulphate caps or that barren vein such as I showed you from Cerro Moro to find ore systems. And I particularly like the lower grade end members of these carbonate base metal and polymetallic systems. They're my ideas. That's the model as it sits today. As we look at more systems, that continues to evolve, but I hope that's been of some use to you and you can go to it for yourselves.
Video?
And we can handle a few questions.
And we can handle.
And I'll be in, and if you're too shy to ask a question in front of everybody else, we can answer a question over dinner.
Any questions?
The evolution from the high sulphidation to a low, same event or different event?
Same event, continue to evolve. So it's not unusual to see low sulphidation mineralogy overprinting high sulphidation alteration. It's a bit tricky, but it does exist.
So you're saying that the phyllic alteration is pretty much the core of the alteration, but is it retrograde alteration?
Yeah. So it's destructive. So the sericite replaces K feldspar, the magnetite gets buggered up, and so it commonly, although you do get phyllic alteration adjacent to veins and it's throughout the system, but you get this major collapse coming down the side. And if you've got a mental picture of the original David Lowell and Gilbert model, they've got the potassic core growing out to phyllic, going out to propylitic, which was great in the time. This is 1975. But now we realise the phyllic's coming down the side. Colin.
You avoided the Carlin situation, but one of the questions a lot of people have is what alteration do we see in Carlin? Do we see as much mineralisation in our black rocks as in our clearly formed carbonate rocks?
Yeah, no, that's a good question. Oh, sorry, I've been forgetting to repeat the question like I was supposed to. So whoever's watching the video, you'll have to wind back because he asked about the phyllic alteration. The person, Joseph, before him, asked about the evolution from high to lower sulphidation. Sorry about that. Colin asks about the alteration in Carlin systems. Good question, Colin. Terry presented a paper in Adelaide at PACRIM 2004 where he talked about this, and the alteration is essentially low sulphidation going from illite out to smectite and with a kaolin overprint. Because as you know, Terry and I, there's a paper at the symposium that we ran in Terry's honour, and that paper's on my website on mixing as a mechanism of mineral deposition in these systems, and I took the kaolin photos out of the presentation because if I knew I'd fall in love with that and spend too long talking about it. But we do see a lot of cases where if the kaolin enters the system, those low pH waters, if we see kaolin, it's evidence that the low pH waters have entered the system from an eroded acid sulphate cap. They are extremely oxidising and they are a brilliant mechanism of giving us gold deposition. And Terry saw some of his best kaolin grades with kaolin, such as I continue to see some of my best grades with kaolin. So it is essentially low sulphidation epithermal alteration. But you might want to go back to that paper. Pretty sure you would have been at that conference. Yeah, lifetime ago now, wasn't it? Some more, please.
No, quick one. Can you get the sort of propylitic philic styles of alteration forming in different environments, say, intrusion related?
Oh yeah, oh yeah. So you'll get a. Oh, sorry. Well, thank you. Can you get propylitic potassic alteration in different environments? And the answer is yes. The high-level intrusions, subvolcanic intrusions that you get in an epithermal system, they're not as hot. So where I was a few weeks ago, we had low-temperature K feldspar, adularia flooding, grading out to very rare epidote, and then most commonly chlorite. The only thing being, if you got your porphyry, you've got a great big heat source, and so you get good quality potassic alteration with secondary biotite K feldspar grading out to your actinolite epidote chlorite. But if you're higher crustal level and you've just got a dome, they'll be much less. And just as at a higher crustal level, your philic alteration won't be philic, it'll be argillic. Instead of getting high temperature cerussite, you'll get illite. But you might still get a bit of anchorite and you'll certainly get the pyrite. Does that explain it? Yeah.
Yanacocha is a high sulphidation gold deposit.
Yeah,
isn't it?
yeah.
So how come it's so huge? Is it all in the oxidised zone? I understood it wasn't.
Good lad, thank you. Why is Yanacocha a high sulphidation deposit so big? Because A, it's located on a transfer structure in northern Peru, so it's on a big structure that the subduction zone changes across. Thank you to Simon Meldrum. And you've got a big magmatic source. You've got an area that's been active for some period of time. There's outcropping porphyries that have been early, and then the system's been uplifted and they've been eroded, and there's still an active magmatic source down there driving that. So I would say in that structural environment on the transfer structure, we've had a big, long-lived magmatic source that's driving all those high-level intrusions and diatremes. And diatremes are just a great way of getting those fluids from our intrusion source at depth up to a higher crustal level where you can very quickly have metal deposition. A lot of high sulphidation systems.
It's not all oxidised.
Now it's not all oxidised, and I've never quite got to the bottom of why they can heap leach all that stuff.
That's what I was getting.
Yeah, no, that's the gap in my knowledge.